Picture this, you are at a carnival and there's a giant slide that takes you down while a set of stairs leads you up. Which part do you take to reach the prize at the top? In this video, we'll tackle a fascinating challenge where every steps matter. Join us as we cover the secrets of navigating through twists and turns. Can you figure out the fastest way to climb your way to victory? Alright, let's dive into the heart of our solution for the quickest way up challenge. The goal here is to find the minimum number of dice throws needed to reach the 100 square on a board filled with ladders and snakes. So how do we approach this problem step by step? First, let's set up the stage. We define our board size. There are 100 squares. This is the fixed size as we know exactly how many positions we need to cover for as we navigate our way through the game. The target square, of course, is square number 100. Next, we need to handle multiple test cases. This is important because the board configuration, the ladders and snakes can change from one test case to another. We'll read the number of test cases and set up a loop to process each one. This keeps our solution flexible and adaptable to different scenarios. Now let's talk about the board setup. We initialize an array called boards that will help us represent the connection on the board. Initially, each square points to itself, meaning if you land on a square 5, you stay on square 5. However, we need to account for ladders and snakes, which changes this behavior. When we read in the ladder and takes the starting square and the ending square, and we update our board array to reflect this jump. So if there is a ladder from square 3 to square 22, when you land on square 3, you automatically move to square 22. It's a clever twist that alters your path and can significantly change the minimum throws needed. Similarly, as we do the same for snakes, if there is a snake that drags you down from square 17 to square 4, we adjust our board's array accordingly. The key inside here is that these connections create a dynamic landscape on our board, transforming simple moves into strategic jumps and setbacks. Once our board is fully set up, it's time to tackle the core of the problem, finding the minimum number of moves. Here we'll use a technique called B breadth first search or BFS. Why BFS? Because it explores all possibilities layer by layer, ensuring that we find the shortest path in an unweighted graph like our board of squares. We initialize a queue to keep track of our current position and the number of moves taken to get there. Starting from square 1, we mark it as visited and enqueue it with 0 moves. Now, as we perform BFS, we keep pulling the current square from the queue and checking if it's a target square. If it is, we will return the number of moves taken to reach it. If not, we explore all possible dice rolls from 1 to 6. For each possible dice roll, we calculate the next square and check if it is within the bound and it hasn't been visited yet. Here's where it gets interesting. When we land on the next square, we look at our board array to see if there is a snake or ladder. If there is, we move to the destination square indicated by the board. This means our search isn't just about the squares, but also about the shortcuts and setback presented by ladders and snakes. Finally, if we exhaust all possibilities and we haven't reached square 100, we return -1, signaling that it's impossible to get there with the current configuration. So let's recap. We set up our board, read the ladders and snakes, and then apply BFS to navigate through the boards efficiently. Each setup is a technical decision based on the configurations we read in, and that's what makes this problem not just a test for coding skills, but a fun strategic challenge as well. Alright folks, let's quickly recap what we have covered in this video. We tackled the HackerRank challenge, the quickest way up, where we design a C# solution to navigate a game board filled with ladders and snakes. We walk through the code step by step, starting with setting up our board and reading in the number of ladders and snakes. Then we implemented a breadth first search BFS algorithm to efficiently calculate the minimum number of dice rolls needed to reach the target square. Remember, the key takeaway here is how BFS helps us explore all possible paths in a systematic way, ensuring we find the quickest route. Make sure to check the source code link in the description. If you found this solution helpful, don't forget to give it a thumbs up and subscribe for more coding challenges and solutions. Your support keeps us motivated and to create more awesome contents. Stay tuned for our next video where we'll dive deeper into algorithm challenges and explore more advanced techniques that can optimize further our solutions. Happy coding, and I'll see you next time.